Hello everyone, this is Rudro from Vision Graphics and AI team of TCS Research and Innovation Kolkata. And today we are going to describe the Sim2Real challenge approach at CVPR with iGibson. Before we began, we had to choose what approach to take for the three scenarios: the static scene, the interactive scene, and the dynamic scene. And we had to make a few decisions. And here those are. The first one was to start with deterministic path planning algorithms because we were well versed with it, and if required, to switch to learning based algorithms. The second was to find a common state that would not be too dependent on noise or variance between real and simulation phase, and hence we chose geocentric maps because that fit the description. Thirdly, the question was how to create those geocentric maps. Should we infer depth from RGB images, or should we use depth directly? And we decided to use depth directly because in that case it was a lot more invariant to domains, and domain adaptation was not a problem. And penultimately, we also had to find out a way to decide on rules or differences between the static scene and the objects in the interactive scene or the dynamic scene. And hence, we used object detection to make that understanding or make that inference. And we used YOLO for that to detect and interact with them. And finally, when we came to real objects or real images and real depth, we had to find out a way to filter the depth and make the scenes comparable to the simulation scenes. And hence, we handle these inaccuracies not just at the depth image level, but also at the map level. All our starting code and the Brace framework is based upon the Active Neural SLAM framework from the paper Learning to Explore Using Active Neural SLAM that was written by Devendra Chaplot and other authors and was published at ICLR 2020. The first scene or the point nav static scenario is where we are provided with the depth image, the RGB image, and of course, robot's pose, robot's velocity, from which we can infer the robot's pose. Now, starting with these two things, the depth map and the robot's velocity and its pose, we feed the depth map into an egocentric projection, make an egocentric projection by flattening it along the z-axis. And similarly, we feed this egocentric projection and the robot's pose to the neural SLAM module, and we get back the estimated pose that we use with a spatial transform to find out the geocentric map. This geocentric map is fed to a simple deterministic motion planner. In this case, it is the fast marching motion planner, but we can replace with other motion planners as well. And with the goal, we find out a local policy that is made into actions by an imitation learning policy. And more description is available in the Active Neural SLAM paper. Now let us see a demonstration of how it works in the static scene in iGibson. As you can see, the map, the top view constructed from the robot sensors is quite accurate, and the robot is able to avoid the static obstacles and plan a path to the goal. The goal is marked in green, and the red robot is marked along with its trajectory in red. Now, for long goals, the challenge is the drift between the maps and the sensors. And hence, here we use the goal value or the goal reference that is obtained at every frame from the robot's frame of reference and update the goal at every 25th time step so that the drift does not affect the goal position. So when it comes to interactive objects, we still retain the architecture of our static scenario, but we add a few elements. To detect objects, we use RGB along with YOLO object detection, whose reference is provided at the bottom, and it is then used to segment the depth. The bounding box obtained from YOLO is used to segment the depth out of these objects and project them into egocentric projections. Again, like previous examples, we use the egocentric projections and the robot's position to make it into a geocentric projection of the object. Now, in the fast marching motion planner, we augment it to remove those objects from the scene so that our planning or our navigation can happen in spite of these objects. Now, there can be better policies as well, which can be for the scope of work to intelligently remove objects or to assign a cost to it, in which case it will interact only when there is no other option available. Now, let us see how it works in the iGibson setup. As you can see, the interactive objects have a green bounding box around them and are marked in black on the map. Whenever there is an object, it removes them whenever the robot comes to its vicinity. And as a result, it is able to plan a path despite a depth image being there or despite an obstacle being there in its path. Now let us talk about how we tackled dynamic objects. Again, we have the same regular static scenario path planning, but along with it, we have the YOLO object detection for Turtlebot. Here, we must also take care of how the Turtlebot looks in the real world. So we took real imagery from online sources to also fine tune along with whatever data we had from the simulation so that it works on both the scenarios and the objects are detected reliably. When we get the egocentric projection of the turtlebot in every frame, we take a few frames of data to infer what the motion model of the turtlebot is. And we detect what the future positions could be, and we feed all of them to the motion planner so that when we can subtract at every point what the previous position was, when we can add a few future frames so that there is no path planning by our agent through the future frames or future positions of the turtlebot as well. And as a result, we can see that the dynamic obstacles are avoided even better. Now let us see a few examples of the dynamic obstacle avoidance. You can see the turtlebot is detected with a green bounding box and marked with black on the map. Also, when the robot goes out of view, the last position is retained by the map so that we do not go and crash into the robot. Ultimately was the challenge of corrections on noisy data from real world. So we had depth that we obtained from real sense cameras, and we wanted to not have an inaccurate map from them. And we noticed that there was missing depth as well as noisy images. So what we did was for the missing depth, we used an adaptive filter to filter out the very low frequency data from the maps. And for the incorrect depth, we found out that in the map frame or in the map domain, it was easy to segment them using median filters. Now let us see a few demonstrations of how it works. You will see that there are incorrect radial lines drawn from the robot to edges where there was missing depth because they were all zero values, and we also have some noise. Now we have side-by-side comparison of before and after corrections for a few cases, and you'll see that in case with the median filter in the map domain, we see that a lot of noise, almost all of the noise is now gone, and we are able to have a clear path between the agent and the goal. There is still some work to be done in the real domain for us, and we hopefully will be able to work in the coming future. Our team at Research and Innovation, Kolkata, has been able to work on this challenge for the past 1 month and have been able to learn a lot of things. Myself, Rudro, Sandika, Sanjana, Dr. Brojeshwar, who was our guide, and Junaid worked tirelessly to adapt ourselves to this new task and learn a lot of things. Also, along with it, we would want to give our heartfelt thanks to the organizers of the Sim2Real challenge who helped us at every decision and every question that we had without a lot of delay, and also provided us informational insights whenever we needed. For now, thank you so much and hope to see you again next year if this challenge happens.